Hey, welcome back. This is 13.3, and now we're going to do the partial derivatives. So we looked at limits, and we can define the partial derivative in terms of a limit. So that's what we'll do kind of first. The limit definition of the partial derivative. So there's going to be a derivative in sort of the x direction, or the derivative with respect to x, and we define that to be f, and then we put a little x there of x comma y. That will equal the limit as change in x goes to 0 of, and you can kind of see, if you remember the difference quotient from Calc 1, it's kind of like that. So we're kind of adjusting the x variable, but leaving the y variable constant. Okay, so minus f of x y, and then all over change in x. The partial, then the derivative in the direction of y, which we'll call the partial derivative of f with respect to y. In that case, the difference quotient will look like this. We sort of nudge the y, or the change in y, and leave the x constant. And this thing will be our partial derivative, assuming it exists. Okay, so let's use the limit definition to determine the partial derivatives of this multivariable function. F of xy equals 2x minus 5y plus 3. Okay. So first we'll get the partial derivative in the x direction. So fx xy will equal, and what I'm going to do is, well, I need a limit first off. Change of x goes to 0. I'm going to plug in x plus change in x. Okay, so this part of it I shall put first. Okay, so let's see what that's going to be. Wherever I see an x, I'm putting x plus change in x. And then minus 5, leave 5y as it is, and plus 3. So that's that first portion. And then I go ahead and subtract f of xy. Okay. That'll be put right here. Okay, so f of xy, I need to put it in parentheses, try to remind myself to distribute the negative. We're subtracting the entire expression. Okay, so that part is sitting right here. And it's all over change in x. Okay. You can guess as to what your answer is going to be. You're basically, the way you think of it is the x is the variable, but the y is just a constant. And when you take derivatives of constant, it's just equal to 0. So I am guessing that my partial derivative with respect to x is just going to be 2. Okay, so anyways, let's take a look. Limit as change in x goes to 0. Have to do some distribution, a little bit of algebra. Change in x minus 5y plus 3. Distribute minus 2x plus 5y minus 3. All over change in x. 2x's cancel, 5y's cancel, 3's cancel. I get the limit as change in x goes to 0 of 2 change in x over change in x, which is, of course, 2 at all points where change in x is not equal to 0. So we end up with 2, just as I supposed, right? 2 being kind of the coefficient on x up there. Well, it is. It's not kind of. Okay, let's find the partial derivative with respect to y. The same thing, and you could guess what it's going to be, right? It's probably going to be negative 5 right there, that coefficient on your y, because everything else will be considered a constant. The x is a constant, the 3 is a constant. Okay, so let's again set up our limit. So this time we're replacing the y with y plus change in y. So I have then 2x minus 5 times y plus change in y plus 3 minus f of x, which is 2x plus, or rather minus, right? 2x minus 5y minus 5y plus 3. And that would be all over change in y this time. So this would be the limit as change in y goes to 0 of 2x minus 5y minus 5 change in y plus 3 minus 2x plus 5y minus 3 all over change in y. And sure enough, we have a bunch of cancellations. 3, and it looks like I'm going to get -5, just as I supposed. Okay, change in y goes to 0, -5 change in y all over change in y is -5 at the end of the day. Okay, so it kind of works like your old-fashioned derivative. It's just you pretend that one of the variables is a constant, and take the derivative of the constant is just 0. Geometrically, what these things are, and there's some other notations. So notice some notation for the partial derivative. Instead of using the d all over dx, so before the derivative would be df over dx. Now we're going to use these weird curly d's, and my d's kind of look like this. It's the way I draw them. So I have the partial derivative of f with respect to x. And I think it's just a lowercase delta is what you're looking at right there. Anyways, it's really not too big of a difference. It's just a kind of a reminder that you're dealing with a multivariable expression. Other ways of writing it, of course, we just saw f with a little x there. I guess that's the two major ways we'll see here. Okay, so just those two ways. We don't use the prime notation here. So, anyways, let's start actually doing the computation for partial derivatives instead of doing the limit definitions. So, just finding partial derivatives. And before I get there, geometrically, maybe we should introduce that idea. I said it's basically the slope and direction. So you'll have some sort of surface, and the slope in the x direction is kind of what you're doing is taking the surface and cutting it with a plane in the x direction and looking at the trace on that plane. Then you pick a point on that plane and where the surface is being cut by that plane, and you find the slope on that at that point. Okay, so in that figure 13.28, so just maybe section 2, let's call it the geometry of it. And let me draw my own picture rather than using their picture, because I already have a picture in the hopper, so to speak. So let me just get that out of the way. All right, so I'm going to have this plane in the x direction, so this will be that partial derivative with respect to x, and it's cutting through some sort of Twinkie-shaped object like this. Maybe the other side of it is kind of like this. Right, so this maybe is in 3 dimensions. This. So the derivative with respect to x, the partial derivative of this surface with respect to x, what you're doing is cutting the surface with a plane in the direction of the x-axis, and then you're kind of looking at the trace on that plane. So here I took that plane and kind of just laid it on its back, and I look at the trace in that picture. So maybe it looks like this. And you could pick a point on that trace, and then you could figure out the slope at that point. Okay. So you're going to need an x and a y to really figure it out, and you'll see that in some of the problems. They'll say evaluate the partial derivative at this point, and then you'll get your answer. But yeah, that's kind of the geometry. Let's look at the geometry in the other with respect to the other axis. Let's see if I can kind of pull this out a bit. So in the x direction, Let's use our Twinkie again. Maybe we're sort of cutting the Twinkie in half this time. Okay, so this plane now, sorry, it's going in the y direction now. Okay. Get my axes drawn. So this is the x direction, and this is the y direction. This is our z. Again, you could take this plane and, you know, it's basically what you kind of see there is the trace. But I'll lay it out just for going through the motions. So you'll have your trace of the Twinkie in the YZ plane, and you can pick a point on that and figure out the slope at that point. So these partial derivatives are giving you slopes. Okay. It's just in order to get that slope, we have to kind of do a slice and consider the trace. Okay. So hopefully that makes some sense with respect to the geometry. Let's look at their picture. Maybe that'll help a little bit more. And we'll see it again when we go through the exercise. But you can see in the x direction, the red thing is the surface here on the right. And then we cut it with a plane. And then we'll find the slope of at this point of the trace. Okay. So there's this trace. It kind of looks like a high parabolic type curve in the trace, and then you designate a point in there, and you can get a slope in the x direction. And then likewise here, I'm cutting the surface with a plane in the y direction. That's thought of as a partial derivative in the y direction, with a partial derivative with respect to y. And again, you see you're cutting the surface, and you're picking up a point on the trace and finding the slope there. Okay, so hopefully that gives you some intuition. It's probably weird to you right now, but that's the idea. Okay, so let's now go to actually doing derivatives like we would in calculus without the limit. So you have all your like power rule and chain rule and product rule, quotient rule. All that stuff will apply here. You just pretend that one of the variables is a constant. So finding partial derivatives, this is example 1. The function given is 3x minus x squared y squared plus 2x cubed y. And we want to find the partial derivative with respect to x and the partial derivative with respect to y. If you don't mind, I'm not going to write the x, y every time. It just gets a bit annoying. Okay, so with respect to x, the first term here, the derivative of 3x is just 3. Okay? The second term, the only variable part is this x squared part. Okay? This y squared thing, you just consider that as a constant, and you don't take the derivative of it. So you're going to get negative minus 2x y squared. So you just leave that y squared alone like it's a constant. And then on the last guy, again, the only variable part you consider is the x cubed. So you basically just take the derivative of that part, and you're going to get plus 6x squared y. Okay? So that's the partial with respect to x. Now let's do the partial with respect to y. Because so looking at the 3x now, because x is considered a constant, it's like taking the derivative of 3. Okay, and it's just going to be 0. The next term then, the only variable part is the y squared. So you just leave the x squared alone. The derivative of y squared is 2y, so I'm going to end up with 2x squared y. And then the last term here, the only variable part is the y. So you leave the 2x cubed alone, and then the derivative of y is just 1, so you just end up with 2x cubed. Okay. That was part A. Let's look at part B. Their function this time is a product of two functions. ln of x is a little more complicated, right? Times sine of x squared y. Okay. So first I'll do the partial with respect to x. Both functions given in the product are functions of x. So I have to do a product rule. The first guy, the derivative, I'll take the derivative of ln x first. So that's just 1 over x, and then leave the sign of x squared y alone. And then plus, now you leave ln of x alone, take the derivative of sine of x squared y. So the derivative of sine x squared y, first it's cosine of x squared y, and then you tack on the derivative of the guts of cosine, right? So that's just going to be, with respect to x, 2xy. Then clean it up a little bit. Let's clean it up first. So I get 1 over x sine of x squared y plus, I'm going to put the constants and stuff up front, 2xy ln x times the cosine of x squared y. You may want to use some parentheses to indicate that the cosine is not inside the natural log. Okay, let's go to the derivative with respect to y. So this time, that first term there, the ln x part, is just a constant now, okay? So you need not use the product rule. You just can leave the ln of x alone and then take the derivative of sine of x squared y. So that would be now cosine of x squared y, and then the derivative of x squared y with respect to y, that's just going to be x squared. Okay? So it's going to be x squared times ln x times the cosine of x squared y. Okay. So really, I think, not too big of a deal. Let's do one where we are actually evaluating the partial derivative. So look at example 2. It gives the function f of xy equals x e to the x squared y. They want you to get the 2 partial derivatives and then evaluate at the point 1 ln 2. So first get fx. In this case, both functions, it's a product of 2 functions, right? And both are in terms of x. So we're going to go ahead and use the product rule. So first I'll take the derivative of x, which is just 1, and leave e to the x squared y alone, plus leave x alone, and then the derivative of e to the x squared y is e to the x squared y right back, but then you have to tack on the derivative of x squared y because of the chain rule. So with respect to x, you take the derivative of the x squared part, which is 2x, and you leave the y alone. Okay. Let's rewrite it so it looks a little prettier. I have e to the x squared y plus x e to the, whoops, I'm not listening to myself. Cat is bothering me. 2x times x is 2x squared, y e to the x squared y. Let's go ahead and evaluate it then. It's going to be one of the problems with me not writing the x comma y every time. It makes this a little confusing, but plugging in 1 comma ln 2, I'll have e to the 1 squared is 1 times y, which is ln 2, plus x is 2 times 1 times ln 2 times e to the x squared y, which again is going to just be ln 2. You can simplify e to the ln 2 is just 2, and then plus this part is on to it. It's on its own there, but that part will equal just 2. So you'd end up with 2 times 2, which is 4, and then ln 2. Okay, let's get the partial derivative with respect to y. So in this case, it'll be, you don't have to worry about the product rule because that x is just a constant. So you're going to have x e to the x squared y, and then times the derivative of x squared y with respect to y is just going to be x squared. So you end up getting x cubed e to the x squared y. Then I need to evaluate this thing at 1 comma ln 2, and plugging in 1, you get 1, and then e to the ln 2 again. So you're just going to get, in that case, 2. Did they give you a nice picture? I think this is the picture for it, maybe, this thing. We kind of already looked at those pictures, but anyways. Finding slopes of a surface. So I mean, that's what we just did. We found the slope of this on this surface in the y direction and the slope on the surface in the x direction. This is just another exercise in that regards. I guess we could still do it. Let's do it just for the sake of doing it. Let's make this one the video quiz for the day as well. Let's get that out of the way before I forget, like I did in the last two videos. So this is then 13.3, and I'm doing example 3 from the book. Okay. Get it all marked down, ready to go. Okay, so our function, our surface this time is negative x squared over 2 minus y squared plus 25/8. They want you to figure out what the slope is in the x and y directions at the point 1/2, 1, 2. So let's get the partial derivative with respect to x. That will be from the first term negative 2x over 2, so that would be negative x. And then the derivative of y squared will be 0. The derivative of 25/8 will be 0 as well. So the derivative in the x direction is just going to be negative 1/2. The slope in the x direction will just be negative 1/2. Then in the partial derivative with respect to y, so that's going to be this time negative 2y, and then the slope in the y direction on this surface is just going to be negative 2. Okay. Yay. And then they give you a nice little picture here, and you can see in the x direction, it's variable depending on which x you pick. We've set the y variable to be 2, so you know, you're going forward 1/2 and then over 2, and then you see you have a slope in the x direction. But there's also one in the y direction. It looks like it's, if you put it there, it'd be negative, right? In particular, it's negative 2. So if you look here, the slope in the y direction, yeah, it looks like it's negative 2. So it's going downwards, you know. Okay, so in other words, there's two slopes if you think about it on this object. So the object kind of looks like this. There's going to be the slope as you cut it in the x direction, but then also a slope as you cut it in the y direction right here. So there's two different slopes at this one point. There's this one slope kind of going like this, and then there's this other slope kind of going like this. So it's different than what you have right in Calc 1, where you just have one slope at every point. But now you're having basically an infinite number of slopes. You can describe them later on. We'll be describing tangent planes. Okay? So if you spun that little slope tick mark there, the red thing, if you like flicked it and spun it around, it would kind of form a tangent plane at that point. But we'll get there eventually. Okay, so anyways, we got another finding slope problem on the surface. Okay, might as well get some more practice, right? Example 4. Maybe we should do one from the homework. I haven't been really doing my homework lately. I hope you don't mind. Let's go ahead and do number 12 here. Maybe this will be more informative than. Okay, so we have something that looks like we're going to need like a quotient rule on it. I need to evaluate the partial derivatives at -9, -9. All right, so the partial derivative with respect to x. I'm going to have to do a quotient rule on this guy because the numerator is in terms of x and the denominator is in terms of x. So I go low times the derivative of the high with respect to x, that'll just give you a y, minus high times the derivative of the low. So that's just going to be 1 all over the low squared, x minus y squared. simplify this. So you get xy minus y squared minus xy all over x minus y squared. And then you can simplify that. It'll be y squared all over x minus y squared. And then, of course, evaluate it to get the slope in the x direction. And you put in 9 in the top, negative 9 in the top. Negative 9 squared is 81. In the bottom, you have 9 minus negative 9, which is 18 squared. I'm not figuring that out. I don't know. So what is this? 9 times 9, all 18 is 9 times 2 times 9 times 2. There, that wasn't that hard. I don't know why I complain so much. I don't know what my problem is. Okay, so fy, the derivative with respect to y. Again, I got to do a chain rule. So the derivative of the high with respect to y is just x minus the high. The derivative of the low with respect to y is going to be negative 1 all over the low squared. That will be x squared minus xy plus xy all over x minus, look familiar, x minus 1 y squared. So it's x squared all over x minus y squared. Kind of looks just like the other guy, but with an x in the top. Let's evaluate it. So it should be the same thing, right? I'm betting it's the same thing. I'm not even going to do the math. I don't care at this point, right? All right, I can. Let's go ahead and plop it in. So we get y squared divided by x minus y squared. This is 1/4. This will be y squared. Oops, x. Oh, whoops. Okay, whatever. Squared divided by x minus y squared. 1/4. 1/4. I don't know why it's being a jerk. Maybe it doesn't like the parentheses. My f of x is wrong. Low d high minus high d low. Derivative of low with respect to 1 all over x minus y squared. Xy minus y squared. Oh, I lost a minus. I apologize. Even the cat is upset about it. So there's a negative there. Negative there. I shouldn't be using the software to check my answers. I should get it right on the first try. I know. Okay, it's okay. All right, so more of that baloney. Using partials to find the rate of change. So, you know, that's just a matter of getting the partial derivative and substituting in. Let's see what else we have. Okay, so partial derivatives of 3 or more variables. Let's see what section I'm on. 2. Well, I'm actually on 4 then, right? So this would have been 3. Now I'm on 4. So now we're looking at 3 or more variables. And it's basically the same thing. You just let one of the variables be variable and then consider the other 2 constant. So looking at example 6, we have the function f of x, y, z equals xy plus y z squared plus x z. Let's get the partial. First off, get the partial with respect to z. They want you to do z and I guess probably x and then probably y. I don't know. Let's get the partial with respect to z first, okay? So part A, the partial of f with respect to z will equal, so the first term will just be 0 because there's no z there. It's just constant. The second term will be 2yz, and then the third term will be x. Okay, so yay. Part B, oh, okay, they give you a different function, f of x, y, z equals z sine of xy squared plus 2z. All right, so this time the partial with respect to z, let's just write fz equals, I'm going to have to do a product rule and then a chain rule. So first taking the derivative of z, I just get sine of xy squared plus 2z. Then leave z alone. The derivative of sine is cosine of xy squared plus 2z. And then the chain rule, I have to tack on the derivative of cosine, the guts of cosine. So tacking on with respect to z, the xy squared is 0. The 2z will just become 2. Cleaning, I get sine of xy squared plus 2z plus 2z cosine of xy squared plus 2z. Okay. Alrighty, no big deal really. Let's do part C then. Partial derivative. This has 4 variables. We want the partial derivative with respect to w. So you have 4 of f of x, y, z, w equals x plus y plus z all over w. Because we're finding the derivative with respect to w, I'm going to rewrite this as basically a constant, x plus y plus z times the w to the negative 1. So the derivative, you could just use the power rule, bring down negative. You get x plus y plus z, and then w to the negative 1 minus 1 is negative 2. So you get negative x plus y plus z, which you can distribute all over w squared. That's what you want to do. So no big deal there. Higher order partial derivatives. So now you remember back in Calc 2, you could keep taking the derivative over and over. You get the second derivative, the third derivative. You could do that here, but you can, on top of that, you can also mix and match the variable you take the derivative with respect to. So you could first take the derivative with respect to x, then take the derivative with respect to y, and then the derivative with respect to x again, and so on and so forth. And you don't have to do any particular order. You can do whatever order you want. Okay, so the one weird thing is maybe the notation. So this is section 5, I think. Higher order partial derivatives. So if I want to do like the derivative with respect to x and then with respect to x again, it'll be like this. So here's the derivative of f with respect to x. Then I'm taking the derivative of that with respect to x. So the way I would write that would be this curly d squared f all over dx squared. Okay. And then another way you can write that is f. So I did x first, and then I did x again. So the inner one is the one you do first. and when you use this notation, sort of the outer one is kind of the one you do first in this other notation. So if you did first the partial derivative with respect to x, and then you took the partial derivative of that with respect to y, it's like the inner one is, or sorry, the outer one here, I guess you could think of it, the one to the right, the rightmost is the one you did first. But then when you go to your other notation, you will have to write it f, you did x first, and then you did y. So the one you did first is on the left. Okay, so hopefully that's not too far of a bridge. It's just a little annoying. And generally, you know, you'll know the difference. Because okay, so anyways, let's try to, and this remark, they're kind of noting that that difference between the two versions. Okay, and I have been known to screw them up once in a while, so it happens. Anyways, let's look at example 7, and we want to find the second partial derivatives. So now instead of just you know, one second derivative, there's basically 4 second derivatives. So anyways, our function is 3xy squared minus 2y plus 5x squared y squared. We want to evaluate the partial derivative, the mixed partial here at -1, 2, the derivative with respect to x and then y. So let's go at it. So first, I'm going to find the derivative with respect to x. So I'll have 3y squared plus 10xy squared. Then I'm going to use this to get fxx. So you take the derivative with respect to x again. That first term is 0. Then you get 10y squared. Then I'm going to find the derivative of the partial derivative of f with respect to x with respect to y. So I take the derivative of this thing with respect to y to get this thing. All right, so this would end up being 6y plus 20xy. Okay, so on the other hand, let's begin with fy. All right, so this time I'll do the first term is 6xy, the second term minus 2, the third term plus 10x squared y. So far so good. Then take the derivative of that again with respect to y. So that would be 6x, the minus 2 is 0 then, and then plus 10x squared. Okay, and then I'll take the derivative of this thing with respect to x, x. So that will be 6y, the 2's gone, and then plus 20xy. And there are our 4 partial derivatives. Okay, they wanted to figure out what is fxy of -1, 2. And so I plug that into here, and that will give me 12 minus, I guess, 40. Okay, so that would be -28. Just for kicks, let's find fyx. And what is that? So I plug in 2 for y, I get 12. And then, well, they're the same, aren't they? Okay, that's not just some miracle of science or coincident, a major coincidence or something. This generally will happen when your functions are really nicely behaved, and it's theorem 13.3. Okay, so theorem 13.3 is on the equality of mixed partials. Basically says if f is a function of x and y such that st is such that fxy and fyx are continuous on some region, some disk R for every xy in that R, then the 2 mixed partials are the same. So f of xy of x comma y will in fact equal fyx of xy, just like we saw in the previous example, right? This guy is the same as this guy. Right, and you can tell that the original function we're given is basically the polynomial version of a multivariable function. And back in Calc 1, we noted all polynomials are really nicely behaved. So you kind of expect this one to be really nicely behaved as well. And in fact, we have that criteria fulfilled, so we have the equivalence of the mixed partials. Okay. You can play this game then with higher order functions. We won't be getting too carried away with that, but let's just take a look at it for the sake of completeness. fxyz. My cat is like, really? Do you have to show them how to do this? Can't you just feed me? Yeah, we're going to go through this, okay? So I need f, and we're showing the kind of equivalence of these partials. Fxz we want to show is equal to fzx, And then we want to show that fxzz is equal to fzxz, which is equal to fzzx. Okay. And you see in the note up here, when it says also applies to functions of 3 or more variables as long as the second partial derivatives are continuous, and all the second partial derivatives are continuous. Then each point in R, the order of the differentiation and the mixed second partials is irrelevant. If the third partial derivatives are also continuous, then the order of the differentiation of the mixed partial third derivatives is irrelevant. Okay, so let's take a look. First get fx, so that's going to be y e to the x plus lnz, and then fxz is going to be, take the derivative of that with respect to z, that'll just be 1 over z. Fz is going to be x over z, and then fzx will be, you know, if you rewrite this as 1 over z times x, that 1 over z is a constant, so the derivative of x is 1, and you just get 1 over z. So yeah, those are, in fact, equivalent. Let's get fxz z, so fxz and then z again, that'll just be -1 all over z squared, because 1 over z is z to the -1, so you bring down the -1 minus 1 in the exponent, -2, so you get that. Let's look at zxz, and for this guy, and notice it's not really continuous everywhere, right? It does have its limit, its restrictions. You can't let z be 0. It's not continuous there. But it's saying that these guys will be equivalent for where it is continuous. Okay, so where it's not continuous, you're kind of just not paying any attention. But this function is continuous in other intervals, right? It's continuous from yeah. Okay. So anyways, with z again, this is just going to be -1 over z squared. What's the other one we need? Zz and then x. So I need fzz. Fzz is 1 over z. No, sorry. Fzz is the derivative of this with respect to z, right? So that'd be -1 over z squared times x. And then fzzx is just going to be -1 over z squared. So all 3 of those are good to go. Okay, I think maybe that's about it. Yeah, and that goes in the homework. Okay, so thank you for watching as usual, and we shall see you next time.